Welcome back. Last time we derived the equation for a turbine efficiency, and today we will derive the equation for nozzle efficiency. For example, we have a converging duct, and it is a control volume because it has mass transfer. Inlet we call number 1, and outlet we call number 2. It's a control volume. What a nozzle does is to increase the velocity of the fluid. How does it achieve that goal? You can take a look at mass flow equation. Mass flow rate m dot is equal to rho VA. Rho is density, V is velocity of the fluid, and A is cross-sectional area. If the system is at a steady state, the mass flow rate, the left-hand side, doesn't change. It's constant. And then let's say the fluid is incompressible, so the density does not change. And now A is the cross-sectional area. How does the cross-sectional area change from 1 to 2? It's becoming smaller and smaller, so cross-sectional area becomes smaller. In order to make this equal sign still valid, what has to happen to velocity is velocity has to go up. So this is how a nozzle achieves increasing the velocity of the fluid, which is the purpose of the nozzle. How do we measure the efficiency of a nozzle? We use eta, nozzle. Okay, so the definition is 1 over 2 V2 squared over 1 over 2 V2S squared. V2 is the fluid velocity at number 2, and V2S is the velocity of the fluid at number 2 if the process is isentropic. V2S must be greater than V2 because V2S is isentropic, which means ideal, while V2 is for the actual process. So the numerator is the kinetic energy at surface number 2 for the actual process. And denominator is the kinetic energy at surface number 2 when it is isentropic. Isentropic process must be able to give you a higher V2. So that's why it's the denominator.